Drone operation is being replaced. Commercial UAVs are now adopting onboard artificial intelligence as the primary method for flight and navigation. This line graph maps the projected growth of the U.S. artificial intelligence drone market. Starting at $4.13 billion in 2025, the market climbs to $12.64 billion by 2033. This capital shift indicates that the industry is prioritizing software-driven autonomy over manual flight control. As these systems take over, the primary value of a drone operation moves from the pilot's manual dexterity to the system's software capability. This shift is moving even faster as the Federal Aviation Administration expands authorizations for BVLOS operations. BVLOS stands for Beyond Visual Line of Sight, an aviation term meaning the aircraft flies distances so great the operator can no longer physically see it. In the commercial airspace of 2026, the demand for remote control pilots is being superseded by a need for operators who can oversee these self-sufficient systems. To understand how a drone replaces a human pilot, we have to look at its internal data processing architecture. Modern UAVs are packed with sophisticated sensor arrays and central processors that evaluate their environment constantly. Two pillars make this autonomy possible: computer vision and predictive analytics. Computer vision is an AI technology that allows systems to automatically identify and track objects from digital images, while predictive analytics uses data algorithms to anticipate future outcomes, like equipment degradation, before a failure occurs. However, early autonomous systems hit a bottleneck. Because they relied on cloud computing, the drone had to beam its sensor data up to a distant server and wait for instructions back, creating a communication delay during active flight. This comparative flow model demonstrates how edge computing solves that delay. Edge computing is a distributed IT architecture that moves processing power directly onto the drone itself, rather than a distant server. Because it evaluates data locally, it detects threats instantly and executes split-second navigation without waiting for a cloud connection. Severing the tether to the cloud allows these aircraft to execute complex operations in highly remote environments. It makes unassisted long-distance missions, like inspecting hundreds of miles of rural pipeline, entirely viable. That onboard intelligence also enables operators to scale operations from single aircraft to coordinated networks deployed across wide territories. Today, these fleets operate using swarm intelligence. Swarm intelligence is a system design inspired by biological flocks and colonies, where multiple autonomous units communicate constantly to act as a single unified network. In agriculture, a swarm dynamically maps enormous tracts of land. The individual units divide the labor to simultaneously track crop health, locate pest infestations, and measure soil moisture, entirely on their own. Public safety agencies use these exact same networks for disaster response. Multiple drones coordinate systematic search grids, rapidly mapping damaged areas and sharing the real-time locations of survivors with ground teams. The energy sector relies on these autonomous fleets to scale up infrastructure checks. A coordinated group can execute complex thermal inspections of wind turbines or power lines simultaneously, cross-referencing their data on the fly. Coordinated swarms consolidate data from multiple points, providing a real-time situational awareness grid that operates at a scale humans cannot replicate. Because these advanced fleets require heavy capital and technical expertise, the industry is pivoting toward drone as a service. Drone as a service, or DaaS, is a business model where a provider handles the hardware, piloting, and compliance on a subscription basis, eliminating the need for clients to buy their own aircraft. This breakdown chart illustrates the scope of the DaaS market, projected to command $27 billion by 2033. The core service components, specialized hardware, data analytics, and regulatory compliance are expanding, while the traditional hardware ownership segment shrinks. Organizations are adopting this model because the specialized AI analytics and the volume of harvested data are now more valuable than simply possessing the drone itself. This reality creates challenges for smaller operations. Developing sophisticated AI hardware in-house is expensive, and managing massive amounts of high-resolution sensor data introduces privacy liabilities and cybersecurity vulnerabilities. Aviation authorities are also working to keep pace with the technology. Regulators are currently drafting the frameworks needed to govern massive swarm deployments and autonomous air traffic systems. To remain competitive, operators must prioritize AI literacy. Rather than attempting to build expensive local systems, many smaller operations will need to evaluate strategic partnerships with established AI technology providers. Operators must also focus on highly complex, specialized scenarios. Where routine inspections become fully automated, human expertise is still required to supervise the AI and manage exceptional situations. The value in the drone industry has shifted from the physical act of flying to the management of intelligence. Success belongs to those who adapt their skills to navigate an automated sky.